Welcome to this problem walkthrough. Today, we'll be tackling the problem Count the Number of Consistent Strings, a fun challenge that combines string manipulation and set operations. We'll explore the problem step by step, understand the underlying intuition, and discuss potential approaches to solve it efficiently. Let's dive in. In this problem, you are tasked with counting the number of consistent strings in an array. We are given two inputs: first, a string called aloud that consists of distinct lowercase English letters, and second, an array of strings called words. A string from the words array is considered consistent if every character in that string is present in the aloud string. The goal is to find and return the total number of consistent strings in the words array. For the input format, aloud is a single string where all characters are unique, and words is an array of strings that only contain lowercase English letters. The output should be a single integer representing the count of consistent strings. Let's look at an example to better understand this. In the first example, the input aloud is ab and the array words contains the strings ad, bd, ab, ba, badab. The output is 2, meaning there are two consistent strings in the words array. Here's why: the strings ab and ba are consistent because all their characters are present in the aloud string ab. However, ad and bd include the character d, which is not an aloud, and badab also contains d, so these are not consistent. This example highlights that to be consistent, a word must not contain any character outside the aloud string. Now, consider another example. In the second example, the input aloud is ABC and the array words contains the strings A, B, C, AB, AC, BC, ABC. The output is 7, as all 7 strings in the words array are consistent. This is because every character in each word is a subset of the characters in the aloud string ABC. In the third example, the input aloud is CAD and the words array contains CC, ACD, B, BA, BIG, BAD, AC, D. The output is 4, as only CC, ACD, AC, and D are consistent strings. These strings only contain characters from the aloud string CAD. The other words include characters like B that are not in aloud, making them inconsistent. This demonstrates how we filter words based on the aloud string. The problem also specifies certain constraints to keep in mind. The length of aloud is between 1 and 26, meaning it can include up to all lowercase letters. The words array can contain up to 10,000 strings, and each string in words has a maximum length of 10. Additionally, the aloud string is guaranteed to have distinct characters, and both aloud and words only consist of lowercase English letters. Let's also consider some edge cases. For example, if aloud is A and words only contains A, the output is 1 because the only word matches the aloud set. If aloud includes all 26 letters and words contain strings like ABC or hello, the output would count all words since they are subsets of aloud. On the other hand, if aloud is A and words contains B, C, D, the output would be 0 because none of the words are consistent. Finally, the solution must handle large inputs efficiently, where the words array is close to its maximum size and each string is at its maximum length. To begin, let's explore the brute force approach to solving this problem. The idea here is simple: for each word in the words array, we iterate through its characters and check whether each one exists in the aloud string. If all characters in the word are found in aloud, we increment the count of consistent strings. This approach involves nested loops, one to iterate over the words and another to check each character against aloud. While straightforward, this method is not very efficient. The time complexity is n*m*k, where n is the number of words, m is the average length of a word, and k is the length of the aloud string. This inefficiency arises because we repeatedly check membership in aloud, which becomes costly as the input size increases. Additionally, the space complexity is minimal, at 1. However, as the dataset grows, the performance of this approach degrades significantly, making it unsuitable for larger inputs. Now, let's consider a more efficient solution using a set. Instead of repeatedly checking each character against the aloud string, we can pre-process aloud into a set of characters. This pre-processing step allows us to perform membership checks in constant time, 1. The process is straightforward. First, we convert aloud into a set. Then, for each word in words, we iterate through its characters and verify that they all exist in the set. If they do, we increment the count of consistent strings. The time complexity of this approach is O, n*m, where n is the number of words and m is the average word length. This is because the membership checks are now constant time operations, and we avoid unnecessary repetitions. The space complexity is O, k, where k is the length of the allowed string, as we store its characters in the set. Overall, this approach is significantly faster than the brute force method and is easier to implement compared to more advanced techniques. For cases where memory usage is a critical concern, we can optimize further with a bit masking approach. Here, instead of using a set, we represent the allowed characters as bits in an integer. Each character corresponds to a specific bit position, with a mapping to the least significant bit, b to the next, and so on. To implement this, we first compute a bit mask for allowed by setting the relevant bits for each character. Then, for each word in words, we calculate its bit mask by setting the bits for its characters. By performing a bitwise an operation between the word's bit mask and the allowed bit mask, we can determine if all the word's characters are valid. The time complexity remains O, and *m, but the space complexity drops to O, 1, as the bit mask representation is fixed in size. This method is extremely memory efficient and leverages the speed of bitwise operations. However, it is limited to lowercase English letters and can be harder to understand and implement, making it less intuitive for general use. After considering the trade-offs, we chose the optimized approach using a set as the best strategy for this problem. It strikes a balance between simplicity, efficiency, and practicality. While the bit masking approach is more memory efficient, the additional complexity it introduces is unnecessary for most use cases. The set-based solution is intuitive, easy to implement, and performs well within the given constraints. By pre-processing allowed into a set, we achieve significant time savings over the brute force approach, without introducing excessive complexity. Overall, the set-based approach offers an ideal combination of clarity, speed, and scalability, making it the most practical choice for solving this problem effectively. To solve this problem, we need to determine how many strings in the array words consist only of characters from the string allowed. Let's break this down step by step. First, we need to understand the input and output. The input consists of a string allowed and an array of strings called words. For example, if allowed is ABC and words is B, ABC, ACD, then we want to count how many of these words are made up entirely of the characters B and C. In this case, the valid words are B and ABC, so the output would be 3. Next, we move on to the first step of our algorithm, which is to convert the allowed string into a set. By creating a set, we can store each character from allowed in a way that allows for fast membership testing. For instance, if allowed is ABC, the corresponding set would be BC. Using a set is advantageous because it allows us to check if a character exists in allowed in constant time, on average, instead of iterating through the string repeatedly. This optimization is key to making our solution efficient. Now, we proceed by iterating through each word in the words array. For each word, our goal is to check if all its characters are present in the allowed_set. This can be done efficiently using a helper function or a Python one-liner like all, char in allowed_set for char in word. What this does is iterate through each character in the word and verify if it exists in the set. If all characters pass the check, we increment a counter that keeps track of valid words. Once we've processed all the words, the counter will hold the final result, which we return as the output. There are a few important insights here. First, by using a set, membership checks are significantly faster, avoiding the performance cost of repeatedly traversing the allowed string. Second, the all function short circuits, meaning it stops checking as soon as it encounters an invalid character. This reduces unnecessary operations, making the algorithm more efficient. Lastly, checking each word character by character allows us to discard invalid words early, saving both time and resources. Let's examine the data structures and complexity of this approach. We use two main data structures. The first is the set allowed_set, which stores the allowed characters. This set is highly efficient for membership testing and has minimal memory overhead since the maximum size of allowed is limited to 26 characters for the English alphabet. The second is a counter variable, which is used to track the number of valid words. This is a simple integer that requires constant space. For the time complexity, let's break it down. If n is the number of words and m is the average length of the words, creating the allowed underscore set takes k time, where k is the length of the allowed string. Checking each word involves one membership check per character, which is m, and doing this for all words results in a total of n asterisk m. Therefore, the overall time complexity is k plus n asterisk m. For space complexity, the allowed underscore set requires k space, and since everything else is constant, the overall space complexity is k. This makes the solution both time and space efficient for the given problem. Finally, let's discuss some edge cases and walk through an example. First, consider the case where the input is empty. If allowed is an empty string, no word can be valid, so we would return 0. Similarly, if the words array is empty, we return 0 because there are no words to check. Another scenario is when none of the characters in words overlap with the allowed characters. In this case, no word is valid, and the result is also 0. On the other hand, if all words consist entirely of characters from allowed, the output would simply be the length of the words array. Now, let's revisit our earlier example with allowed equals ABC and words equals B, ABC, ACD. We first convert allowed into the set B, C, and initialize count to 0. For each word, we check its characters. The word it is valid, so we increment count to 1. The word B is also valid, so count becomes 2. The word ABC is valid as well, so count increases to 3. However, the word ACD contains the character D, which is not an allowed underscore set, so it is skipped. At the end, the counter holds the value 3, which is our final result. This Python implementation solves LeetCode problem number 1684, count the number of consistent strings. The function count consistent strings determines how many strings in the words list are consistent with the allowed string. A consistent string contains only characters from allowed. Explanation of the code. First, the allowed string is converted into a set called allowed underscore set. Sets allow for efficient membership testing, ensuring we can quickly verify if a character belongs to allowed in constant time. A variable consistent underscore count is initialized to 0. This variable will store the count of consistent strings as we iterate through words. The function then loops through each word in the words list. For each word, the all function checks if all characters in the word exist in allowed underscore set. The all function iterates through the characters of the word and evaluates if each character is part of allowed underscore set. If the current word is consistent, the consistent underscore count is increment by 1. Finally, the function returns consistent underscore count, which contains the total number of consistent strings in words. Key points. Set conversion. Converting the allowed string into a set optimizes membership checks, as set lookups are significantly faster than searching in a string. Efficiency. The algorithm processes each word and character in the input, making the complexity proportional to the sum of the lengths of all strings in words. This ensures the solution is efficient. Edge cases. The code handles edge cases such as empty words or allowed gracefully. If allowed is empty, the result will correctly be 0 since no word can be consistent. Similarly, if words is empty, the function will return 0 as there are no words to check. This implementation balances clarity and efficiency, effectively solving the problem within the constraints. Here, we start by importing the necessary classes from the Java utility package, as we'll be using a hash set to store the allowed characters. In the method count consistent strings, the first step is to convert the allowed string into a set. This is done using a hash set, which allows for quick lookup of characters. By iterating through the allowed string and adding each character to the allowed set, we ensure that we have a collection of all valid characters. Next, we initialize a counter variable, consistent count, to 0. This will keep track of the total number of consistent strings. Now, we begin iterating through each word in the words array. For each word, we assume it is consistent by setting a Boolean variable is consistent to true. We then check each character in the word to see if it is present in the allowed set. If we encounter a character that is not in the set, we immediately set is consistent to false and break out of the loop, as the word cannot be considered consistent. Once the inner loop completes, we check the value of is consistent. If it remains true, meaning all characters in the word were found in the allowed set, we increment the consistent count by 1. After processing all the words in the array, the method returns the value of consistent count, which represents the total number of consistent strings. This implementation is efficient because the use of a hash set ensures constant time complexity for character lookups, and we exit the inner loop as soon as we confirm a word is not consistent. Overall, this approach balances clarity and performance, making it a straightforward solution to the problem. In this example, the input allowed is given as the string ib, and the words array contains add, bd, ab, ba, badab. To solve the problem, the first step is to convert the allowed string into a set for quick lookup of characters. This gives us allowed underscore set equals a b. Next, we initialize a variable consistent underscore count to 0, which will keep track of the number of consistent strings. Now, let's process each word in the words array. Starting with the first word, add, we check if all its characters are in allowed underscore set. While the character A is in the set, D is not. This means add is not a consistent string, so consistent underscore count remains 0. The next word, bd, is checked similarly. Here, B is in the set, but D is not, so bd is also not consistent, and consistent underscore count stays at 0. Moving on to ob, all its characters and b are in the allowed underscore set. This makes ob a consistent string, and we increment consistent underscore count to 1. Next, we process the word ba. All of its characters b, and a are found in allowed underscore set, so it is a consistent string. We increment consistent underscore count to 2. Then we check the word badab. While b and a are in the allowed underscore set, the character d is not. This makes badab inconsistent, so consistent underscore count remains at 2. After processing all the words, the final output for this example is 2. Let's now look at another example. Here, the input allowed is ABC, and the words array is a, B, C, B, AC, BC, ABC, ABCD. Once again, we start by converting allowed into a set, giving us allowed underscore set equals a, B, C. We reset consistent underscore count to 0 and begin processing each word in the list. Starting with the first word, a, we check if all of its characters are in allowed underscore set. The character A is indeed in the set, so A is consistent, and we increment consistent underscore count to 1. For the next word, B, its only character B is also in the set, making it consistent. We increment consistent underscore count to 2. The word C is checked next, and since C is in the allowed underscore set, it is consistent as well, and consistent underscore count becomes 3. Then, we process AB. Both of its characters, A and B, are found in the set, so AB is consistent, and we increment consistent underscore count to 4. Similarly, for AC, both A and C are in the set, making it consistent and increasing consistent underscore count to 5. The word BC follows, and since both B and C are in the set, it's consistent, and consistent underscore count rises to 6. Finally, for the word ABC, all its characters of B and C are found in the allowed underscore set. This makes ABC consistent, and we increment consistent underscore count to 7. Now, we check the last word in this example, ABCD. Here, while A, B, and C are in the set, the character D is not. This means ABCD is not consistent, so consistent underscore count remains 7. After processing all the words, the final output for this example is 7. Let's move to one more example to reinforce the concept. This time, the input allowed is XYZ, and the words array is X, Y, Z, XY, XC, YZ, XYZ, XYZ. As before, we start by converting allowed into a set, resulting in allowed underscore set equals X, Y, Z. We initialize consistent underscore count to 0 and begin evaluating each word. First, we check the word X. Its only character, X, is in allowed underscore set, so it's consistent, and we increment consistent underscore count to 1. Next, for the word Y, its character Y is also in the set, making it consistent and increasing consistent underscore count to 2. The word Z is checked next, and since Z is in the set, it's consistent as well, and consistent underscore count becomes 3. For the word XY, both X and Y are in the set, so it's consistent, and we increment consistent underscore count to 4. The word XZ is similar, with both X and Z being in the set, so it's consistent, and consistent underscore count rises to 5. For YZ, both Y and Z are in the set, making it consistent and increasing consistent underscore count to 6. The word XYZ follows, and since all its characters X, Y, and Z are in the set, it's consistent, and consistent underscore count becomes 7. Finally, Zyza includes the character A, which is not in the set, so it's not consistent. The final output for this example is 7. To evaluate the time complexity of this solution, we start by analyzing the process step by step. First, converting the allowed string into a set requires iterating through each character in the string. If the length of allowed is k, then this operation runs in k time. Next, we loop through the list of words, which contains n words in total. For each word, we need to determine if it is consistent. This involves checking every character in the word against the characters in the allowed set. If the average length of a word is m, then this consistency check requires m membership lookups in the set. Since Python sets allow for constant time membership checks on average, this step takes m time for a single word. Repeating this for all n words makes the total time complexity for this step n*m. Now, combining these steps, we can see that converting allowed to a set requires k, while the iteration over words and the consistency checks together contribute n*m. This means the overall time complexity of the solution is k plus n*m. Next, let's analyze the space complexity. The primary additional space usage comes from the creation of the set allowed_set, which stores all unique characters from allowed. Since there are at most 26 unique lowercase English letters, the space required for allowed_set is constant, or 1. However, we also need to account for the input itself. The allowed string and the words in the list occupy memory proportional to their lengths, which adds up to k plus n*m. Additionally, the algorithm uses a few auxiliary variables, such as consistent underscore count to track the number of consistent words and word to represent each word during iteration. These variables require 1 space. Similarly, the generator used to check membership, char_n allowed_set for char_n word, evaluates lazily and does not consume additional space beyond 1. As such, the overall space complexity is k plus n*m, which is dominated by the storage of the input. When comparing this to a brute force approach, the optimized solution shows a clear advantage. A naive method would iterate over all characters in allowed for every character in every word, resulting in a time complexity of n*m*k. By leveraging Python sets for 1 membership checks, the optimized approach reduces the time complexity to k plus n*m, eliminating the dependency on k during the consistency checks. Now, let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, all words consist of characters from the allowed set, meaning the membership checks are straightforward and require minimal processing. However, even in this scenario, the algorithm still needs to process all n words and m characters per word, so the complexity remains k plus n*m. In the worst case, none of the words are consistent, which forces the algorithm to evaluate every character of every word against the allowed set. Despite this, the overall complexity does not change and remains k plus n*m. Mathematically, the dominant term in the complexity comes from the nested iteration over words and the characters within each word. Each character contributes 1 for the set membership check, leading to n*m for the entire iteration. Adding the k required for the allowed set creation gives us the final time complexity of k plus n*m, consistent across all scenarios. One common pitfall when solving this problem is neglecting to validate edge cases. For instance, you might encounter situations where the allowed string is empty or the words array has no elements. Overlooking these scenarios can lead to runtime errors or unexpected outputs. To address this, always make sure to handle edge cases like empty inputs, single character strings, or duplicate characters in the allowed string. Another mistake is using inefficient character lookups. If you repeatedly check whether a character exists in the allowed string using the n operator, you end up with a time complexity of n*m, where n is the number of words and m is the average length of each word. A better approach is to convert the allowed string into a set, which allows for 1 lookups. Finally, some people tend to overcomplicate their solutions, introducing unnecessary nested loops or data structures. This adds both time and space overhead. The key is to keep the solution simple and focus on direct comparisons and efficient operations. Another mistake to be mindful of is assuming that all strings are lowercase or ignoring case sensitivity altogether. If the problem specifies lowercase letters, it's crucial to ensure your solution adheres to this requirement. Case mismatches can lead to incorrect behavior, so always validate inputs and confirm assumptions, especially during an interview. Additionally, it's important not to overlook duplicate words in the words array. Even if duplicates exist, they should still be processed, as skipping them could result in an incorrect count of consistent strings. The solution should treat each word independently unless explicitly instructed otherwise. These considerations will help you avoid common pitfalls and produce a more robust implementation. When solving this problem in an interview setting, there are a few strategies to keep in mind. First, always clarify assumptions. For example, confirm constraints like the input size, the character types, and whether the allowed string is guaranteed to be non-empty. This ensures you're aligned with the expectations and can design an appropriate solution. For larger inputs, such as when words are allowed can contain tens of thousands of elements, consider discussing efficiency improvements early. Using a set for O1 lookups is a great optimization to bring up. Breaking the problem into smaller, modular tasks is another effective strategy. For instance, you could create a helper function to check if a word is valid based on the allowed string. This modular approach not only makes your solution cleaner but also easier to test and debug. Lastly, if you propose alternative solutions, communicate the trade-offs clearly. Explain why you might prioritize time complexity over space complexity, or vice versa, depending on the constraints and input size. If you're looking to practice similar problems that build on the concepts used here, there are several related LeetCode problems worth exploring. For example, LeetCode 1426, Count Elements with Strictly Smaller and Greater Elements, challenges you to work with comparisons and counts. LeetCode 2023, Number of Pairs of Strings with Concatenation Equal to Target, involves string manipulations and efficient handling of pairs. LeetCode 392, is Subsequence, focuses on validating character sequences efficiently, and LeetCode 20, Valid Parentheses, emphasizes working with stacks and validations. These problems share skills such as character validation, efficient string operations, and the use of sets or hash maps, making them excellent practice to reinforce your understanding and problem-solving techniques. There are also alternative approaches you can explore for solving this problem, each with its own trade-offs. One advanced technique is bit masking. Here, you represent the allowed string as a bit mask, with each character corresponding to a specific bit in an integer. This allows for quick lookups and operations, but it adds complexity and is more suited for advanced interviews. Another approach is filtering using Python's all function with a set.isSubset method. These methods are concise and Pythonic, making the code easy to read, but they may be slower for very large inputs. A third option is pre-computing validity. You can create a lookup table for all possible words based on the allowed string and then check each word against this table. While this approach is extremely fast for repeated queries, it is memory intensive and only applicable in specific scenarios where such a trade-off is justified. Each method has its strengths and weaknesses, so understanding the context and constraints of the problem will help you choose the most appropriate solution. Great job making it to the end. In this walkthrough, we summarized the key points of the problem and explored the importance of efficiency in algorithm design. Remember to keep practicing and challenging yourself with similar problems. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!